Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Triangulation is brought to you by Cashfly at CACHEFLY.com.
This is Triangulation, episode 104, recorded May 22nd, 2013. Eric Drexler and Nanotechnology. Welcome to Triangulation, the show where each week we sit down with somebody brilliant, somebody interesting, somebody who's changing the world to talk about big ideas. I look forward to this every week. We call it Triangulation because it's me, a guest, and you. And if you're watching live and you're in our chat room, please make sure you've got your questions ready. We have a guest you're going to want to talk to and find out more about. Eric Drexler is kind of a legend. He's been around a long time writing about nanotechnology. He has 3 degrees from MIT in a bachelor's in interdisciplinary sciences, a master's in astro and aerospace engineering, and a PhD from MIT Media Lab. He wrote, I think, one of the earliest books, I think it was back in 1992, about nanotechnology, molecular machinery, manufacturing, and computation, which was awarded the best computer science book of 1992. And I'm thrilled to talk to Eric. We talked to him on Tech TV many moons ago about nanotech, and I think we've made some strides in the intervening time. So welcome, Eric Drexler, to Triangulation. It's great to talk to you.
Thank you. Good to be here.
Eric's got a new book called Radical Abundance. It's another nanotech book, how a revolution in nanotechnology will change civilization. First, what is the definition that you like to use for nanotechnology?
Well, the first thing I point out is that it doesn't have a clear definition. When I introduced the term, it was in reference to a potential technology of highly productive machine systems based on small atomically precise parts that would make atomically precise products. Then people got very excited. Ideas went in all different directions. And today, the term refers to either that or, well, among other things, small particles, like very fine dust particles. And the path from very clear meaning having to do with an advanced production technology to one that refers just to nanoscale products has been a long and somewhat confusing path.
We've seen I remember when we were in Tech TV late 90s talking about this, people would say, well, the uncertainty principle means you can't, reliably manufacture something in a molecular level. And that's all been proven not true because we've seen widespread use in industry now of MEMS, molecular machinery. Would MEMS qualify as nanotech?
Well, it usually refers to micro electromechanical systems, which are much, much larger, actually. They're based on the semiconductor technologies.
Giant nanotech.
Yeah, the main nanotechnology today is the nanotechnology we're using right now. It's the nanotechnology that makes cell phones possible. That's the underpinning of the entire digital information revolution. It's based on large numbers of nanoscale devices.
You mean transistors in processors?
They're now smaller than the largest molecular structures that people build, and they're measured in tens of nanometers.
That's right.
They're deep into the area that is used commonly to define nanotechnology.
Right. We're seeing 22 nanometer fabs right now.
Yep.
And so that's nanotech, isn't it? Boy, it's almost hard. In fact, some even thought that Moore's law would come to an end soon because we're so small now, you can't get any smaller.
I think it actually is approaching an end.
Yeah.
One indication of that is that in flash memory, traditional scaling has been to make devices smaller. Now they're starting to stack them.
Right.
And that doesn't scale the same way, and it sort of suggests that they're beginning to hit a limit.
We're seeing graphene. In fact, somebody made graphene with, I think it was a DVD drive spinning. That's a molecular level technology, isn't it?
1 atom thick.
Wow. Hard to imagine anything smaller than that. And what is that used for? Is that a superconductor?
It's a very good material, more like a semiconductor, not a superconductor.
Okay.
What I find most exciting about it is its mechanical properties. It's very strong, stiff, smooth, and a good material for making nanoscale machines. You can make bearings and rods and all sorts of useful components for doing mechanical work.
So you must feel a little bit vindicated, because I know when in the early days of what you were writing, people were somewhat skeptical about all this, but it's now happened.
There have been a lot of steps. The most important steps toward this atomically precise nanotechnology, which is really where the long-term promise lies. And there's an enormous amount being done now in many different directions. But long-term, it's about atomic precision. And there's been a funny thing that's happened there, which is that the main areas of progress are not called nanotechnology, and I think that's confusing to people. They don't appreciate how far the technologies have come because they don't wear the label.
Right. Well, tell us about that. What is the cutting edge of nanotechnology now, since 22 nanometer processes are just commonplace?
Well, again, there are, I guess I would say, three kinds of nanotechnology. One is the small particle kind of nanotechnology. Another is the semiconductor nanoelectronics kind of nanotechnology. And the third is prospective, atomically precise production systems and products. And those three are remarkably far apart. They have some overlaps, but what they have in common is smaller than their differences in many ways. So you ask about where the real progress is. The progress that excites me most is in atomically precise systems, and that's in the molecular sciences, where, well, let's see, it's been going on a long time. Started small and has been getting larger, which is what happens when you start at the bottom with atoms. Over a century ago, chemists were making atomically precise structures by organic chemical synthesis. That was a few dozen atoms. Recently, that style of production has reached a scale of millions of atoms. Atomically precise structures that have, up to a million times what the early ones did, and are complex enough and have enough parts that they're starting to look like they might be able to serve as nanoscale circuit boards for nanoscale components that might then plug into chips.
So are these molecular size machines? They're mechanical.
Well, there are all sorts of different structures and applications. Electronic applications, optical, mechanical, chemical. But, well, when looking at where technology is going, it's important to ask what's central.
Yeah.
And what's central are machines that build the things we use. If you look around yourself, you'll find almost everything is something made by a machine.
Right.
Well, where did those machines come from? Well, they were made with the help of other machines. And where did those come from? Well, if you trace it back, you find the lathes and drill presses and computer-controlled milling machines and so on that collectively can make all the parts needed to make more machines like that. And that's really the core of our industrial civilization in some sense. But where did they come from? Well, they were made by somewhat similar but less sophisticated machines in previous decades. And where did those come from? Well, less sophisticated, simpler machines decades before that. And if you trace it back far enough, you find a blacksmith hammering away on a piece of iron and making better tools and passing them on to the next generation.
Smaller and smaller and smaller and smaller and smaller. You, in fact, in the very earliest days of your writings, I think you talked about something called a nanotech assembler. The idea that these machines could and I guess at each stage they get smaller. Is that the idea?
Well, actually, again, you're starting at the bottom. If your building blocks are atoms and molecules, the challenge isn't to get smaller, it's to get larger.
Right.
Larger structures with precision, control, increasing complexity, increasing function.
Start with simple
really
complexities.
The opposite direction.
Yeah, that makes sense. So you're building up from a nanotech size.
Exactly.
Give me some examples. Is some of this stuff being done now?
Well, the atomically precise molecular engineering certainly is, as I say. There's now work that has gotten up to a scale of hundreds of nanometers, millions of atoms, hundreds of distinct places where there are sockets that you can address and install components. That's the cutting edge right now, is learning to use that potential and actually do that. But again, looking at this core of technology question, the question is, we're sort of at the blacksmith stage right now. Well, what's the next generation of tools look like? Not the next generation of products, which is interesting and where a lot of the action is going to be, but looking downstream, the question is, what kinds of tools can we build with the tools that we have? And then what can we build with those tools? And if you look in that direction, pretty soon you start asking, what does physics tell us? What are the limits that physical law implies for what can be accomplished. And part of the reason that people still read what I wrote in 1986, a book called Engines of Creation, they still read that as a book on the future of technology because it wasn't about trends. It was about what physics, which is changeless, timeless, what physics can tell us about the contours of technology when it becomes really advanced.
Can you give us some examples right now, stuff that's being done this way? And of course, we're going to talk about what's coming in the future, because I think radical abundance is more about what's coming.
Again, this is a question of using tools to build better tools, and we don't have those better tools yet. So you can't get the products of those really advanced technologies until you have those. You mentioned earlier that I had come from an aerospace engineering background, and after that, actually, the book that you mentioned was actually based on my MIT doctoral dissertation. But back in the space days, I spent a lot of time thinking about how technology evolved there. And if you'd asked early on, people said, well, we're going to be able to reach the moon and bring back, big boxes with hundreds of kilograms of moon rocks. Well, if people had asked at the outset, can you show us just a few small moon rocks? Well, that would be the wrong question. The question is how high and how far and how fast can you launch those rockets?
Right.
And what's your path in developing from there to a system that finally actually gets there and returns something?
Right.
So it's analogous to that.
Yeah, that makes sense. The reason I keep asking is I'm trying to concretize this, so maybe we can talk then a little speculatively about what it might look like when we get into this age of radical abundance. And where does this abundance come from?
Well, what we can do in the world depends on what we can make. And today, the means that we have for manufacturing are really remarkably crude compared to what's possible. I think there's an analogy here that I think works very well. It's got physics behind it. It's got experience behind it. Today's manufacturing is like analog electronics. Okay? Imagine great big vacuum tubes handling signals at a low speed, all very large scale, and always approximate, never quite right. Digital systems, on the other hand, are always exactly right or exactly wrong. And if you engineer them right, they stay on the right side of things, and the ones and zeros produce the next pattern of ones and zeros that you want. It's the right set. So where we are today is that we've gone from big, bulky, crude, sloppy analog systems to nanoscale devices that handle information in its smallest discrete pieces, in bits and bytes. The prospect now is going from today's big, sloppy, approximate manufacturing to a technology that can be thought of as being like a factory on a chip. Instead of having billions of nanoscale electronic devices processing bits and bytes, you'd have billions or more mechanical devices that process matter at the scale of atoms and molecules. And again, very fast. Electronics works at billions of cycles per second. Machines are slower. It's only millions of cycles per second. But that sure beats what you see in factories today.
Yeah. Where is this work being done right now? Is it everywhere? Or is it specialized areas?
And where we are right now is people developing those better tools. Right. And you find in academia, industrial research labs, government labs, all around the world, people are working on a range of nanotechnologies, including some that are these atomically precise technologies. And a lot of the work is being done, as I said, not in an area called nanotechnology, but in the molecular sciences. And so the applications turn up in science journals where they're talking about biomedicine, or people just trying to understand what you can do with biomolecules. A lot of the work is in biomolecules.
So let's talk about some of the implications. Medicine, it sounds like, would be one area where this would be very important.
I have many atoms out of place here. We have an earplug failure. There we go.
That's a few billion atoms. It's just jumped.
That's about 10 to the 23rd atoms or something, something around there. Yeah.
Wow.
Cubic centimeters, about 10 to the 23rd.
Euronerd in our chat room is saying, is this a good field to encourage kids to learn about, and what should they learn about if they'd like to help build this next generation of tools?
Well, I think it's going to be growing, it's going to be exciting, it's going to be an important way to make a contribution to the world and to global problems, which can be addressed by new, highly productive technologies, problems the scale of climate change, energy supply, resource scarcity, global development. And the path there, from an educational point of view, is it's a matter of understanding the relevant science and engineering principles. Today, what's needed more than anything else is to bring an engineering approach into the molecular world, where today it's been a sort of a domain for scientists who want to discover things, make little demos. But if you want to go from the equivalent of demonstrating transistors to demonstrating microprocessors, at some point you have to have an engineering approach.
Right.
So we need people who are trained, people who studied, to understand the molecular world, a lot of math and physics there, and to understand what it means to think like an engineer, not to seek out problems to study, but to avoid problems as much as possible so as to be able to build things that work.
You make that distinction in your book, Radical Abundance, between the scientist, who is it's kind of knowledge, and to the engineer it's about building something.
Yeah, and those are, in a sense, actually opposite. People, here we have a civilization that's based on science and engineering, and people think that they're maybe the same, that maybe engineering is a kind of science, but it isn't. Scientists look at the world, and they use instruments to get information, and they take that information and they use it to make descriptions of the world. And then they use those descriptions to help guide building general theories. Engineers start with very general ideas, but they're design concepts. They refine those into descriptions, blueprints, designs, and then they use machines, they use manufacturing methods to take the descriptions and make material objects. So you've got information flowing from matter to mind in science,
right,
and from mind to matter in engineering.
That's fair, yeah.
Speak similar languages, but they're really opposite.
Right. That's an interesting clarification. So I always thought of engineering as really just applied science, but it's a different approach to the same information.
Yeah. Engineers certainly apply science, but it's not science.
Different goal. Yeah. So we do have a little bit of a model for the kind of explosive change this can happen thanks to the information revolution and to the microcosm of transistors and microprocessors. As they got smaller, they got cheaper, they got faster, they got better. Almost the reverse of what we're used to in the physical world. So I think maybe now, as opposed to 1986, when you wrote your first book, it's maybe a little bit more understood that we could see a revolution here that could happen very rapidly. What do you think is the time frame for these kinds of sudden changes?
Well,
because I imagine it expands quickly. There's a hockey stick here.
Yeah, very much so. If you look at Moore's law, there has been an exponential growth going on for decades, and that is part of what has given people a sense of the possibilities for rapid and large-scale change. In fact, coming out of the nanoscale world, and there are a lot of parallels in this case. You can think of an atomically precise manufacturing system, APM system, as a factory, but a very compact factory where you can put a system on a desktop that could make anything from a cell phone to a roll of photovoltaics to components which, when snapped together, make an automobile. You might want a larger machine for that, for convenience. And that resembles desktop printing, which takes, arranges pixels under computer control to make images. It resembles 3D printing, which arranges little bits of matter in 3D patterns to make objects. And it resembles information processing itself in that you're using very small devices to arrange small bits of something, literally bits in the case of information, at high speed and in patterns where you download them from the internet. Today we have specialized equipment for making things. Today we have generalized equipment for handling information. The prospect here is to get generalized equipment for making things. So that's the parallel that is going to be emerging. And I think that what we've seen in the information age, including some of the change in economics, decentralization, individuals and small groups being able to make contributions in this domain, we'll see that translate increasingly into the material world when certain thresholds of capability are reached. Again, the returning the moon rock doesn't happen until you're pretty far along the path.
And I know Ray Kurzweil is a supporter of yours. He always talks about the singularity in information technology. Sounds like there is a nanotech singularity, too.
Well, it's a strong feedback process. Right now, it's very straightforward to design and understand the kinds of devices that can be built with an advanced technology of this sort. It turns out that it's harder to understand and design the components that can be made today.
Right.
So we have
we can
things
see
that are easy to design.
We can see the end point. We don't know how to get there.
We can see the end point, and we have a survey of a path to get there.
Right.
But it's like being able to see a mountain in the distance. You can't see all the detail, but you can see the size, shape. Using spectroscopy, you can figure out something about the rocks. And there's a path between here and there, but there are a lot of hills and forest and so on. And experience says you can cover ground like that, but it hasn't been done yet. You can't really map it until you're closer. So there's a lot of underbrush and hilly terrain between here and there, but we know where the there is. We know how large the mountains are. We know what they look like, at least in part, the parts that are facing us in this analogy. And well, let's see. It's hard to predict how long it's going to take to cover the ground, but you can see what the distance is, and it's maybe not so far. And in this case, we also know that the ground gets easier to traverse further along. As tools get better, modeling gets better, engineering methodologies get worked through, it's pretty clear that you're going to see a rapid acceleration. You can't use chips directly to make new chips. Here's a case where the things that are like the chips can be used directly to make the better next generation chips. And we've never seen a technology roll forward before in an environment where the design and simulation capabilities are enormous and can be deployed in advance of the manufacturing technologies. We've seen just a taste of that, and only recently in history.
Right. Yeah, I think Ray talks about once you reach the singularity, machines start building better machines, and they build it faster than humans could, and faster. But he's, of course, talking about an information technology. But it sounds like it's somewhat like that with these micro machines as well.
There's a very strong analogy.
Yeah.
One difference here is that in the case of machines and machine intelligence, no one knows quite what it would look like to do that.
Right.
What are the parts? How do they fit together?
Right.
In this case, what we're talking about is essentially remarkably like taking an ordinary factory and transposing it into a smaller scale. Small gears are gears.
Right.
Small bearings are bearings. Small shafts are shafts. Small motors are motors. They work together. It's just the sizes are smaller, the time constants are smaller, and a whole lot of details, of course, are smaller. But engineers make machines out of different materials on different sizes. They use glue and rivets and snaps and fasteners and all sorts of ways of putting things together. Molecular bonds are just another way. They're not that different from what engineers already work with in manufacturing. And if you can get into a domain, when you get to a level of technology where the components are as simple and robust and straightforward as pieces of the steel machinery that are used today, then a lot of the lessons that have been learned in the last hundreds of years of making steel machines turn out to translate directly. It's really kind of shockingly direct. Part of what radical abundance is about is making it clear just how good that model is and the extent to which someone who's familiar with ordinary technology can, in a certain range of technologies here, apply their knowledge with confidence and actually get a good quantitative sense of what can be done. So it's not a bunch of mystery and nonsense. It's taking familiar principles, textbook physics, and asking, what can we do with those when we have the tools to make the devices?
Right. Forgive me, because I'm not a physicist, and this is a silly layman's question, but it sounds like these are Newtonian devices. And are we not using Newtonian devices at a more of a quantum scale? Is there a problem there?
Well, the fact that you're getting down into the size range where sometimes quantum effects are important is one of the reasons that Sometimes people felt there's something kind of mysterious that have been reluctant to try to think about it.
Right.
But it turns out that electrons on this scale behave in a way where you have to use quantum mechanics. They're lightweight particles, and they wave function spread out. And that's what gives atoms their size and shape and bonds. That's all about quantum electronics. But, atoms can be represented as sort of soft spheres without thinking about the electrons. Bonds can be represented as springs without thinking directly about the electrons. And so on and so forth. So it turns out that in the molecular world, there are two kinds of computational quantum chemistry. One is, computational molecular modeling. One is quantum chemistry, which is all about the wave functions and electrons. And the other one says, well, okay, let's level up and ask, how do the atoms and molecules move under the forces that come from that underlying domain? And what's the result? Well, it's Newtonian, as you say. There are masses, atoms have mass. There are forces. And scientists use, computational modelers use Newton's laws. And just as you plot the course of a spacecraft under the influence of gravity, so you can plot the path of motion of atoms and molecules under the influence of these forces that ultimately come from electrical forces among electrons.
So you have two models, but they're not inconsistent, and
the quantum chemistry tells you what the forces are that
Right.
guide how the atoms and molecules move.
Right.
That's the short story.
Are there useful
you
quantum?
can go off into subtleties in different directions.
Yeah,
but that's
and
the
it's way
basic
beyond
story.
me. But so I apologize. Are there useful quantum effects though that you might take advantage of in addition to the Newtonian?
For manufacturing and the mechanical side of things, the answer is, I think, pretty clearly no. There may be some surprises, things that could be used, but the basic processes are essentially classical. The only thing that's strongly unfamiliar is that everything's moving thermally, have the thermal motions, which are a major engineering constraint. People said, maybe that'll keep you from doing things. Well, you run the numbers. This is all about running the numbers. And those are all quite feasible to work with.
And these are atomic, not molecular, so we can't really say what these materials are because they're just atoms.
Well,
Is that right?
Make something useful, you have to put a fair number of them together. You
Okay.
want to make something with size and shape and so on.
So
At that point,
is it steel? Is it carbon fiber?
Well,
What is it?
more like carbon fiber.
Buckyballs?
The materials, well, they're kind of simple and round. Might find some use for them, but I haven't really seen what it is yet. Carbon nanotubes are a better example.
Right.
They're like a material, graphite, or these long sheets of graphene, but rolled into a cylinder. So it's one atom thick. It's a cylinder, but you can make a picture of it, and the picture shows something that's like a rolled up piece of chicken wire. If you look at the skeleton, and if you represent the atoms, then it's a slightly corrugated, smooth surface. And sure enough, you put one of those inside another, two smooth surfaces nested around each other, and you have a bearing. So that's an example of something which is, on one side, you can think of it as a material. The carbon atoms are bonded the way that they are in graphite or graphene or similar to what you find in the fullerenes. But it can also be looked at as a molecule. If you take a piece of it, you can count the atoms and look at the bonds, and it's a molecule. Or you can have these pieces put together in a way that has them act as machine parts. So it's a question of what perspective you want to use, and you end up drawing on material science, which has a lot to say about atoms and bonds, because materials are just bunch of atoms and bonds. Use chemistry, and use the principles of machine design also, because they all intersect in a pretty straightforward way once you get oriented to the problem and find out what the simulation tools are that'll give you a good picture of the physics.
We're talking to Eric Drexler, in many ways the father of nanotechnology, certainly an early proponent and popularizer of the idea. Back in 1986, his newest book is called Radical Abundance: How a Revolution in Nanotechnology will change civilization. And we're talking about something that we can see in the distance that isn't necessarily here yet, but we are making the appropriate steps to get there. Some have talked about concern, too, because these devices are so small, they permeate the skin. Is there a biohazard to nanotechnology?
Well, again, we're back to the multiple meanings of the term. The kind of nanotechnology that has gotten most of the attention and has really sort of occupied the namespace in large measure for the last decade or more works with small particles. And as you say, they're very small. They can move through the air. They can move around in water like other small particles, and they can move through skin. If you eat them, they can swallow them. They can end up in blood circulation. Some of these particles move into the brain, and they're another potential toxic hazard. It's another material that could be a problem. But of course, a chip is also an example of nanotechnology, and you don't worry about your chip or a cell phone somehow accidentally getting into your bloodstream and into your brain, unless you have it fired out of a cannon, I suppose, or something that might be helpful.
Safely contained inside the package there.
Yeah, and there's just no small loose pieces. It's a solid. It's an engineering system with all the parts connected. It's not a bag of dust ready to blow around. And similarly with these atomically precise manufacturing systems and typical products, having atomically precise parts doesn't mean that you have a lot of loose stuff blowing around, and therefore it doesn't raise those kinds of concerns. In fact, one of the great advantages of atomically precise manufacturing is that the kind of end-to-end atomically precise control associated with this prospective technology can be extraordinarily clean and controlled. Require environmental regulations and safety regulations to draw lines, but it's the kind of technology that makes it very easy to satisfy very stringent constraints on safety and cleanliness. And speaking of how technology will change civilization, today, looking forward at the 21st century, a lot of people are starting to think that it looks pretty grim. We're starting to see resource scarcity increase and prices increase. Certainly, oil, critical minerals, other areas. The ability of the Earth to absorb some of our outputs, in particular CO2, is getting saturated, and that prospects there are looking worse and worse. And it doesn't seem that our industrial civilization has the technologies needed to fix its own problems. Maybe, but it's looking increasingly dubious. Well, now there's a prospect of a post-industrial manufacturing technology, a way of using, turns out, common resources, not scarce resources, to make clean, high-performance systems at low cost, and among other things, be able to drive far and fast toward renewable energy in the form of photovoltaics, and actually possible to do engineering on a scale that's required to draw down atmospheric CO2. If you didn't do anything, the CO2 we've put in the atmosphere would linger for decades, some of it for more than a century. But with a more powerful ability to do what physics tells us we should be able to do with matter and energy, we can harness solar energy to draw down the CO2 level in a matter of years. It's a larger project that can be undertaken with our present productive technology, rather straightforward if you had the APM, atomically precise manufacturing level of technology. That makes the 21st century look different.
No kidding. No kidding. It's a singularity of its own. Is there an Intel now extant, or maybe it's too early to say, for nanotech?
Well, Intel is, as I say, doing nanotechnology.
Of a certain kind, yeah.
Yeah, it's the most impressive nanotechnology in the world today. It's,
no kidding.
Nanoscale components by the billions that have revolutionized our civilization. And as I say, one way of looking at this prospective revolution is a similar process. Again, nanoscale components, large complex systems, programmable processing. What we've seen in the information revolution, but transposed into a revolution in the material world. And I return to that model again and again in radical abundance because it's very effective. It's a useful tool for thinking. It's not a superficial analogy. It's a deep parallel.
I saw that movie that IBM made, the first molecular movie. Is that a nanotech, an example of nanotech?
I'm not sure. Can you describe it for me?
I have to find it for you. Maybe you can find it, John, to play it. It's the world's smallest movie. I'm sure the chat room.
Yes, I have seen that.
Yeah.
Yeah. What they did was they had a flat, atomically precise surface, a crystal surface with little corrugations like an egg crate, in effect, and moved around eggs from little holes in that surface, little pockets, where the eggs, quote unquote, are atoms, and they're like pixels. You have a device that can image them and move them, and you move them around. It's sort of like stop motion animation, but instead of analog with clay, it's digital with atoms in discrete. There we go, in discrete locations.
This is for data storage, and of course, hard drives are a good example of not only nanotech but of quantum effects used reliably and predictably, which is kind of cool. This is a boy and his atom, and so these little dots, are these atoms?
Yes.
Amazing.
Each of those is an image of an atom.
That's amazing.
Well, when people started making pictures like this, somehow the claims of you can't work with atoms sort of faded away.
Yeah, no kidding.
A lot of objections from the late 1980s that I just don't hear anymore.
Yeah, no, and that's what it strikes me, because I of course read your books and we've talked to you over the decades, and it seems in many ways you're completely vindicated. We're seeing it's happening. And I would love to think that some of this might even start to surface in my lifetime in more dramatic ways. Nanobots to clean up pollution or to scrub our blood of toxins and things like that. Are those? I know we can't see we don't know exactly how long it's going to take us to get to the mountain, but are they 10 years off? 100 years off? How close? You must have some sense of the scale.
Well, first I should emphasize that the center of my work is based on physics and physical principles and engineering, where you can do calculations.
Right.
And you can't do calculations of how long it's going to take people to form an engineering organization, how well funded it will be, what the detailed problems that need to be solved are. No breakthroughs, but a whole lot of sort of like in this other metaphor, like chopping through underbrush. But at a talk that I gave at Oxford, I'm located at Oxford these days, a researcher came up to me afterward and asked, well, how long do I think it'll be to get to some of these more ambitious thresholds, the threshold of some of the really transformative changes? And my response was that I think it will happen sooner than I expect. Then I asked him, that's kind of paradoxical, I said, does that convey a meaning to you? And he said, yes, it does.
I love it. That's a great answer. Neil Stephenson in the Diamond Age.
Feels true,
Neil Stephenson in the Diamond Age talks about the legendary Eric Drexler as the father of this transformed world. You're mentioned often in science fiction, a variety of science fiction, because what you're talking about here does sound like something out of science fiction. I can see many a movie scene where stuff gets built or is automatically created, and of course it would require atomically precise machinery to do this. And so I guess that's why we keep peppering you with that question that I'm sure is the question you dread hearing, which is, well, when, Eric, and what? But I think it's not so hard to imagine what it might be like, and I hope it's sooner than you expect.
Well, I think that at some point there will be a clear idea of pathways, a clear sense that those are mountains that we see. It's not an optical illusion. Yep. It's it's a verifiable result, a consequence of what's already known, textbook science. And that just as we saw a mobilization of effort to develop the vehicles needed to go to the moon, we will see a comparable mobilization of effort to achieve technologies that actually have a lot more impact than that and are probably, speculation now, less expensive to develop because we're not working with such large systems and requiring all the things that make aerospace very expensive.
Right.
So when that kind of clarity and focus arrives, I think that we're going to see some surprising change, in part because even in the sciences, there's not a clear understanding of what can be done because the work is spread over many, many different fields. People are focused on their own, their own studies, their own small structures, their own often studies that are focused on biology rather than on the engineering applications of the same molecular structures. They literally have not put the pieces together, either physically, which is the task that actually gets you somewhere, or before that, conceptually. So one of the messages in Radical Abundance is a description of how much progress there's been, what the obstacles are, and that those obstacles today are largely conceptual and institutional. Mm-hmm. And there's a lot that is in the book that has not been laid out clearly before anywhere. It is, I'm told, clear and readable, maybe even enjoyable, in Radical Abundance. And so I think that it's going to really start a new conversation. And that's my aim, is to start a conversation on this where people begin to consider what a different future might be like, begin to consider how to get there, and follow that process forward, that thinking, that examination, that critical examination to what I think are some pretty obvious conclusions, which say, yeah, there's a there. We can get there. The time frame is not exceedingly long, and the rewards are exceedingly large. And that what's needed is a certain kind of engineering focus in fields that haven't had it before.
You talk in the book about a laptop that costs as much as maybe cardboard or aluminum mm-hmm. foil. And you truly can see how this, just in the same way that the microcosm made computers, orders of magnitude cheaper and faster, doubling every 18 months, you can truly see the same exact kind of exponential change thanks to nanotech. And I do hope that people kind of can start to see the dream. And I think you must have, in the 27 years since you first coined that term, have seen amazing progress. And you must feel somewhat vindicated. There were a lot of naysayers in those early days that, see?
Yep. And a lot of the naysaying in the later days came from people who learned about the subject from science fiction,
right?
Rather than reading the scientific literature. So they said, well, this sounds far out, and maybe there's nothing there, and didn't check the numbers. And if you look at the descriptions of the engineering systems and check the numbers, you come to a very different point of view than if you read the newspapers and science fiction stories and make noise based on impressions from there.
It's exciting. The idea of a garage that could build a car. It's just wonderful. I love it. I'm really glad that we could talk to you again, Eric, after a decade or so, and celebrate the progress towards your vision. And I hope you continue to write. The book Radical Abundance is just out and available now. Amazon has it. How a revolution in nanotechnology will change civilization. It's a very optimistic look at the future, and I'm glad to be a little bit more optimistic, because God knows we need it.
Thank you. It's been a pleasure.
Thank you, Eric Drexler, for joining us on Triangulation. We do Triangulation every Wednesday afternoon, right after This Week in Google, about 3 p.m. Pacific, 6 p.m. Eastern Time, 2200 UTC on twit.tv. Do watch live, because as I said, a lot of the chat room questions make their way into the show. In fact, I really am grateful to the chat room for helping me with the interview today. And if you can't watch live, of course, on-demand audio and video always available. We now have 104 shows in the can. You can get them all at twit.tv/TRI. Better yet, subscribe with iTunes or Zune or whatever Xbox, whatever you use, your Android or iOS device to get podcasts, and that way you'll get the episode right every Wednesday when they come out. Thanks for joining us, and we'll see you next time on Triangulation.